Hi everybody and welcome to this video on APT41 deep dive StealthVector. Yesterday, just as of this recording, I published that I created a new repo, a new repository where I'll be uploading fully annotated APT files for some of the interesting APT samples that I find quite unique. Techniques that are quite not so common to see in crimeware or even in other APT groups. And I set up to this video to share with you some of the insights on these techniques. And so I've already uploaded the fully annotated IDP file along with the sample on my GitHub, so you can go ahead and just download to follow along or just take a look. But for what we're going to be doing today is we're going to be taking a look at following things. So this is kind of like the today's agenda. We're gonna look at the payload decryption routine and how the payload is decrypted and extracted. Because at the end of the day, StealthVector is a C++ shellcode loader that's meant to deliver sort of a more sophisticated malware. It was first discovered, I believe, as of August 2021 by Trend Micro. Um, and you can actually see this here. Let me show you that they have already. You can see this, the hacker news. This is actually them reporting on Dashbox, which is more of an enhanced modified version of StealthVector. They just tended to implement everything custom. And so, for example, for the configuration decryption, instead of using the Microsoft next generation APIs for decryption, just used custom advanced encryption standard implementation for this. And instead of just leaving the strings in plain text, they just encrypted those using advanced encryption standard as well. I might create a video on this later on and show kind of like the evolution and development. But for now, we'll just stick to StealthVector and just focus on the interesting techniques I found. You can probably see that they're saying that I think here they're saying that it was first discovered by this section. Yeah. So it was first documented by Trend Micro in August 2021. Described as a shellcode loader written C++ that's used to deliver Strike Picon and a shellcode endpoint named Scramble Cross. So it's just more of a stager malware that's meant to deliver more sophisticated malware, which can even deliver even more sophisticated malware afterwards. So that's pretty much what what this is going to be doing. So we're going to look at how the payload can be decrypted and extracted. We're going to look at how the payload is injected into the process memory. And so you may have heard of process hollowing or process injection. Um, Let me know in the comments if you don't know. I can just maybe create a video on this, but I'm sure you can find tons of resources in these, but not so many resources on module stumping or DLL hollowing. So this technique is still a code injection technique, but instead of just allocating process memory in the address space of a remote process or even in the local process and just injecting the code into that and transfer execution over, or even creating a new process in suspended mode or and and hollowing the text section and carving out the text section and allocate new memory to inject your code into and then transfer execution over. So basically these are the standard code injection techniques, but I found it using module stumping or TLL hollowing, which few of the red team engagements frameworks out there might possibly use. I think that Rattle in one of its iterations is actually adopting and using that. But I'm not sure about other frameworks. I haven't looked at them. So let me know if you know any other frameworks or even APTs that actually adopt the use of modules. So that's one of these things. And so after it injects its shell code, it's gonna try to disable control flow graph if it's running on a control flow graph aware operating system. So we're gonna go over what control flow, control flow guard. We're gonna go over what control flow guard really is. And it's just an exploit mitigation technique. We'll go over this more in depth, and cover how is it trying to uh, generically but bypass control flow guard to transfer execution to its shell code, without like getting caught or detected. So yeah, that's pretty much all we're gonna be covering for today's video. I wanted to do more of a deep dive version of the shell code loader, but I thought this is gonna take way much time. So I think for the configuration, extraction, decryption, I think this part you can do yourself. Um, and you're more than just welcome to reach out if you have any questions on this. But just let me walk you through this and give you a little bit of context on what we're looking at here. So this is StealthVector, obviously, and if you look at the it's a DLL, so it's not an executable. If you look at the exports, you can see we even have over 120 exports. Uh, um, but surprise, surprise, these exports are pretty much all the same. So these are the duplicate exports that pretty much implement all the same functionality. Um, and it can pretty much easily determine that with something like P Studio. If you open up a sample P Studio, like show you, if you just open up a sample, but it's gonna take quite some time for processing. So um, but if you just open up this and go to the export section, you'll be able to see that. So we're gonna wait in this. And so these are just duplicate exports, which means it doesn't matter which one to start at. And for the actual main function, the TLL main function, go there. Um, you can see nothing interesting is here. It's just checking the region code and you know getting the system time and calculating something, and we enter in this infinite loop here. And so this is something not really malicious at all. Uh, uh, the only use of this is you need to know that this H module, assigned here is just, pretty much gonna be your module handle, which is a point where the TLL is located in virtual memory. Another thing I want to cover before we get going is the timestamp eject used by the loader. So you can definitely see here it's just checking that quote word, and if it's set, then we're gonna execute this function and then close the handle to this quote word. So it looks like this quote word actually is just an object handle. Not sure what object is, but we can figure it out later. But as for the else branch, which is the one that's gonna be executed first, since this can be just set to begin with, this is a global variable. It's for default initialized is this is gonna be false. You can see just let me show you this. You see it's getting the module handle, handle to whatever is the executable that side loaded this DLL or uh, 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 because again this is a China linked state sponsor group, and China state sponsor group have this common of DLL side loading or DL search order for hijacking. And so you can just go on and read more on this, but it's pretty much more of a advanced persistence mechanism to maintain persistence in the system by hijacking the default DLL load order by pretty much exploiting a vulnerability that is it's not going to specify the full path name of the DLL to load, but rather just the name of the DLL. So you can just sort of how spoof it and get it to load into memory. So you see, it's just getting a handle to whatever it's the executable that sideloaded the DLL, uh, and you can definitely see that it's adding offset hex3 C. And so if you're familiar with the P file format, the P structure, you know what an offset of hex3 C, this is the MT headers, the new exe headers of the P file format. And then we're adding an offset of 8 to this. And so if you don't know what I mean is, let me show you this here. So it looks like P Studio has already finished. You can see it identified the 122x ports as duplicates, and so you don't have to go into each one of these yourself. What I want to show you is actually, let me open up this uh, if you're just, I want to show you the offsets and how it's actually checking the timestamp if you're not so much familiar with the format. So you see here, this is the DOS header, the first of the headers of the PFI format, and an offset of hex3C. We have this file address of the new exe header. This is an in-file offset of the new exe headers or MT headers. You can just follow it, and you can definitely see here in this hex editor view that we have the 54500. This is the signature of the MT headers. Following that, we want to add a couple more bytes. You can see the 65A771 3D. This is your signature. Excuse me. This is your timestamp. So you can go to the file header, see at an offset of 108 from the NT headers, because it's just added an offset of 8 from the NT headers. This is the timestamp, which is again 65A771 3D. So why is it actually checking the timestamp of whatever the executable that sideloaded the DL? Probably trying to set it to check or make sure that it's sideloaded by the proper module. So we're gonna need this if we're gonna be debugging this in x64 DPG later on. We're gonna have to bypass this eject somehow. Otherwise, we can just proceed to the actual main function, which should be that function. Only if the check is fulfilled, we're gonna execute this function, which is actually the actual main function. This is where all the cool stuff is actually taking place. So you always want to make sure you get this check, but bypassed. Otherwise, it's gonna return from that function and just exit. And so what we're going to be doing is we're going to now just start looking at, the actual function. There's a lot going on here. But I'm just going to walk you through the configuration decryption real quick just to get context what we're doing here. This is the decryption routine that actually extracts and decrypts the contact. Going into that routine, we have another function that's more of a wrapper function that's actually responsible for the decryption. You see definitely here, this is one of these things that I haven't seen before. It's going to try to compute the ERC32 hash for checksum over the encrypted malware config. And I guess this is so to make sure it's not corrupted. It's just kind of validating the integrity of that encrypted config. This is something I haven't seen before, actually. Let me tell you. And so this is the encrypted config size. This is actually hex 50. So it's just copying this over, and you can see it's subtracting a 1 from this for 2 hex E6. So why do you think is it doing this? Because there's always a limit to the amount of data the CRC32 function can process. So I guess it can process more than hex E6 bytes of data. And so this is actually sort of like sanity checking the size of the data to be hashed, or yeah. So then we're just getting the address of this RTL compute CRC32 function. In the later version, or implementations or developments of APT41. Namely, I'm talking about Dutch Pucks, this one that was discovered by Grit Labs. They used an instead MT5 hash to sanity check or validate the integrity of the data. So here we're using CRC32 checksum in the other implementation of the MD5. But the idea is the same, so that's it. And so you can see here, it's calculating the CRC32 checksum over this hex 50, but plot array. This is the encrypted config. And so you can go ahead and just, maybe dump it out of this file if you want it. But there's no point in doing this because it's going to be decrypted. So we want to access the decrypted config. And so I have already, prepped this for you. If you wanted, I can put it to the GitHub repo as well. This is the encrypted payload that we extracted. This is the decrypted payload. This is the decrypted config. They can open up this here. I think you already have it in the hex editor. Actually, this is missing some bytes because I believe it's like hex 48 or hex 40, but it doesn't matter. We can later on dump it again. So yeah, that's just, the CRC32 checksum, and you see it just comparing that to this hard-coded CRC32 checksum. So this is how it validates the integrity, computes at runtime the CRC32 hash, the encrypted config, compare that to the hard-coded CRC value in the malware to validate the integrity. Then we'll have this config wrapper function. This decrypt config wrapper is the one actually doing the decryption of the encrypted config. And they're using advanced encryption standard cipher block chaining for this particular variant. How do we know this? Well, if you go into this function, you definitely start to see things like pcrypt, which is the which is the DLL that implements the Microsoft Next Generation Crypt 2 APIs. So we're dynamically resolving or loading these functions like pcrypt open algorithm provider, and you can see things like advanced encryption standard here. So this is one of these things that they have definitely try to avoid in their later developments. And instead of hard coding things, they just decrypt them at around time. So they have added like string encryption and decryption to their payload. Also, as we'll see later, APT41 tends to have this red team development style. So they have probably hired like red team malware developers, which can write actually red team malware that tries to bypass EDR solutions and bypass exploit mitigation techniques. At the OS internals level. So yeah, that's what they're after. So you can see it's advanced encryption standard. Also, you see the pcrypt property, which sets the attributes of the advanced encryption standard algorithm. The advanced encryption standard has like these multiple different modes of operations, like the cipher block chaining, the counter mode. Uh, uh, um, I remember I looked at a sample of Lab Productus before that actually implements advanced encryption standard counter mode string decryption. And in their later um, implementations of the loader, they have transitioned to advanced encryption standard. I think cipher feedback mode. You can actually read more in this. You can find the research. Like I think it's released on the killer plug. This is the research on the similarities and differences between Dutch plugs and StealthVector. So this is going to be a nice read if you're interested more in their course of evolution. And so you see it's setting the uh, yeah, decrypts that property here, and yeah, so it's actually invoking that decrypts that property. You can see chaining mode CPC. So this is the advanced encryption is tier mode, and I can see as well the decrypt function. This is the key handle, this is the config size, and the initialization vector. So the initialization vector is hard coded in the malware. As for the one that's used to decrypt the config, I think in the Dash box they're sanity checking not only the config but also uh, 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 the initialization vector hard coded to validate the integrity of as well. But you can see that this comes from this function, which again is just this global variable. This is your initialization vector. Definitely. That's pretty much it for the configuration decryption. You see that the encrypted config goes into this memory. So this is going to be the pointer to a variable that receives a pointer to the buffer that contains the encrypted config, and this is just the length. And then after this, it's the processing the config and kind of copy this over into a global hex 48 memory, which it created an initialize. So that's pretty much it for the configuration part. Uh, um, so I hope it's understandable. Now let's move on to the more interesting ports. I told you that they hire guys that are more of a red team malware developers, and so they tend to implement techniques such as ETW event tracing for one, the bash. But they're using you know uh, a technique which I think most of the eaters can pretty much now detect. I'm not sure, however, about this. They're actually patching one of these main functions that write events registered event providers of ETW. So which is the ETW event write function. And so it's just getting the address of the ETW again, the get module handle, get proc address, this API sequence. It just needs to resolve dynamically API. So and you see, what we're doing is we're changing the permission of the first four parts of the function. So what that means is, we're because the text section, once the loader has already done all the mappings and set the permissions as specified in the section headers, the text section should no longer be writable. It should only be executable. So what we're trying to make here is we're trying to make it execute read write. And so we're trying to make it writable because we're going to patch it later on, as you can see down here with the human copying the ETW patch plates into this location of memory. And we're exactly copying 4 plates, which correspond to the following instructions. It's an XOR, REX, comma, REX, and a return. So this is XORing REX with itself, just setting REX to 0 and return from that function prematurely. So that's pretty much the patch here. They're just changing the permissions of the first 4 bytes, and then they're setting the permissions back normal after the patch. So that's a typical ETW, bypass thing that you might see, elsewhere in other samples. Getting going. It's also trying to check if the user is system. So it retrieves the current username, and then it's just this whole stuff is just an inline this string compare, just comparing these two strings. And you see if it's not system, we go to this function, which then goes to the end of this subprint. And again, you see a lot of ICs here, a lot of post paste indicator of compromise stuff. So this is again one of these things they try to avoid in later developments. They have encrypted their strings. I've seen even malware that tries to generate like names for the new texts at runtime, not just encrypting them. So That's for the check of if user system. Now let's take a look at this. So I can tell you that now I've actually created a couple of structures. One that actually stores like config related information, such as important to where the config uh, the buffer is and the configuration, the decrypted configuration links, and an index which is to traverse the config data. But then I created this other hex 48, which is more of a global configuration structure that the malware uses to kind of guide the execute uh, the process of the malware. So I think this is it for these two structures. So if you go ahead and take a look at that here, it's actually checking the flag at an offset of 8. And so, if you look at the terrific config, this should be offset 8, and I can see the flag here is actually just a 0 or a null. So this is a 0, so not 0 is true, which means this I can tell that this is the one that's actually decrypting and extracting the payload, which is what we wanted to do in the first place. We want to see how the payload is decrypted and extracted. So if you go into that function here, uh, you can even see here that this one here is actually getting the full pass name of the DLL, and if you go down here, can definitely see a create file with access, desired access set to create, and so we're trying to open up a handle to the file. But which file? It's the DLL module, right? So we know that the payload is stored somewhere in the uh, in the DLL in the DLL module. So also one of these things I noticed if you go and take a look at that here, you can see it's got a high entropy value. It's the 7.6, which could be an indication that this is packed malware, but in fact it doesn't look it's packed. It's not packed at all. You can see all the strings and plain text, all the APIs, so it can't ever be packed. But I guess the high entropy stems from the fact that the payload is stored encrypted somewhere in this P file, and it can tell you that pstudio is great enough to tell you that it's stored in the overlay. See the 64, whatever 04, whatever. This is actually the encrypted payload, and we'll extract it. I'll show you how. So this is actually trying to open up a handle to DLL for generic creed. It's validating the handle, and then you see the get file size. It retrieves the load for 4 bytes of the file size, and this is the interesting part. Um, Stored in the config is the payload size and the offset in the TLL to where you can find the payload. So you see here, this is offset 2C and offset 30. So let me show you at an offset of 2C and 30. Let me use the offset 2C here. Yeah, so this is a you can see at an offset of 2C, this is 04021. This doesn't look like an offset. It's a size actually. And I've created this other file here, which is 40210. This is the size of the encrypted payload. It's stored in the decrypted. So it's actually reading the size, reading the in-file offset to the payload. I think this is whatever is the keyword at an offset of hex 30. So if you check this as well, back to our editor, you see this is hex 30. It's a 0202. So this is gonna be your offset in the file. So if you go ahead and just maybe navigate to this offset in the file, this is our DLL. You can see bytes. This program cannot be run in test mode. Typical MC bytes and dash header string. let me Control G, and let's navigate to this offset here. And you can definitely see these are the same plots that were detected by Pew Studio. Again, 6 Ds or 4, 6 Ds or 4, 5, 9, 6, 7. Yeah, so these are the same plots that were detected as stored in the overlay of the file of the DLL. And so, it used to be, back in the days, a common thing to store like maybe payloads and resource sections, and use like maybe, find resource, size of resource, API sequence to extract this from the malware runtime. But now a lot this gives away a lot of indications that, whenever you see this in malware, you know that they're extracting something from the resource config, or even just the seconds for the attack. So now what we're doing is there's just like, you see whatever in between here, just a bunch of null bytes. So this is bytes, definitely. And this should be the end of the DLL. And so it's just stored in the overlay. And the size of this is definitely, I've already extracted that the payload. And I can see the size of this is 40210, which is pretty much what we have here. This is 40210. And so it's actually adding the offset to the size, and it check it against the file size, just making sure we're within boundaries. So we're gonna allocate that much memory equal to the size of the payload. And so it's just allocate that much memory equal to the size of the payload. And we're gonna set the in file pointer to the offset where the encrypted payload is using set file pointer. So this is the file handle. This is the offset where the encrypted payload is. We're going to read that into this buffer we just allocated. This is where the encrypted payload goes. You can see goes into the file as the second parameter. And so this is reading the decrypted the encrypted payload. Then it's actually decrypted down here. Look at this decrypt data function. But this time we're using another hard-coded initialization vector. And so this initialization vector is not the same one, I guess, that we before uh, 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 um, for the decryption of a config. But the structure of the function is pretty much the same. This is the encrypted payload. This is the encrypted size, and this is where the decrypted payload goes. And so um, this is it for the payload decryption. It's standard advanced encryption, standard decryption. It's stored in the overlay. So I have extracted that here. See, this is the encrypted, and this is the decrypted. I've extracted in a debugger, just set a point of that function, and examine the buffer and dumped it from there. And I can see this doesn't look like a standard, you know, the P header. It didn't have like the MZ plights. This program cannot be run in test mode. I can definitely see the MZ plights here, the 4D5A. But this comes later. We have these hex 90s, which correspond to no ups, I think. But I can tell you, if you just uploaded this to VirusTotal or something, this is gonna be recognized as a Cobalt Strike Paycon. It's a Cobalt Strike Paycon, which matches the description we found on the Hacker News when they said that it's used to deliver a more sophisticated malware, either a Cobalt Strike Paycon or this scramble, cross thing. So this is it for the payload decryption. You can go ahead and take a look at that function even further. We have this other function, which I believe it's XOR encrypting the config before uh you see encrypt data here, create file. All right. It doesn't matter. So you can take a look at that function, if you want it. But what matters is we've extracted and prepared the payload that will be executed later. Uh, Now we want to look at how this payload is injected into memory. we're gonna take a look at this module stumping technique and see how this is any different from classic but process injection, process hop techniques. So that's it. Now you can say that this field at an offset of 8 is just instructing the loader to extract and decrypt the payload. So we can just say this is rename it, obviously. Go at an offset of 8. It is. And let's say the D word here is just extract, decrypt, payload. Oh, uh, this is actually extract. Then we have this other check here. Here, and I believe this is the one that has to do with module stumping. Um, yeah, it could be interesting. And this GIP process mitigation policy is the one that has to do with CFG or control full guard. So let's uh let's take a look at that first. So this is checking the flag at hex contact 40. Huh, another flag. So if this is yeah, if this is true, then this is like flag um hex 14, right? So yeah, hex 14. You see, this flag is not set by default, which means we're gonna execute the else. So let me look at the else here, since this is the one that's gonna be executed. But we can look at this later on. I think I did in the fully annotated IDP file if you're interested. Let me go inside of that here. Uh-huh. Right, I think it's all right, I think it's doing this. All right, I think we're gonna take a look at that function. So again, it's checking that D word, but again, this is a D word. A global by default should be 0 initialized, so this is gonna be true. It's getting a module handle RTL get version. So what I think it's getting the operating system version. So in the context of control full guard, control full guard was first introduced, I believe, was when is 8.1, but then was like discontinued the support for, due to some maybe backwards compatibility issues, and they have just enhanced or modified this a little bit and re-implemented this in like later Windows versions. We'll get to this more later, but just uh, it's just trying to check the operating system version to know the correct pattern to use to search for the function that will actually check for the target address to make sure whether or not it's valid. I'll show you what this means later on. So let's see. So I think this is actually setting the size of the structure. This one takes an OS version infrastructure. So let's just retype this to be, I think this is, I think an RTL. Let me see. Yeah, put an RTL with version info. All right. Oh, I think it's let me just copy the name of that one. It's hard. So I think we should not be a pointer. OS info. Sure. So this is setting the size of the structure, and so we need to look it up here. Maybe to see the and let's Chrome here. And we need to look up the definition of that one here. But I think it's not really necessarily important. You see, it's clone RTL get version and just unstick this. It's setting this flag to true here. So this is a flag, obviously. And then we're checking the minor version. We're checking the OS version. You see here, it's adding to the minor version 10 times the major version, and this is less than hex 3. And so it's trying to check the OS version. This holds true. We're gonna go to this. So I'm not sure which version is trying to detect with this one, but we're gonna check the full annotated IDP file for this. Let me see. I think it was not packed properly. For some reason, it looks like it's corrupted. Maybe we copied this. Anyway, it doesn't matter. We know it's trying to check the OS version. Just trying to make sure it's running on an OS aware, we're control full guard OS aware. Because like I said, not all the Windows operating system versions support control full guard. And then we see get current process, definitely, and a get module handle, get proc address. So the get process mitigation policy function. Let's look at that one here. So this retrieves mitigation policy settings for the current process and takes the process handle, which is v10. Obviously, excuse me, v10. Yeah, it takes current process, which should be the get current process return back. So the get current process returns a handle to the current process, which should be the DLL. And the second parameter should be the process mitigation policy, which is one of these constants. So I think this is just let's just hit M to see if we can resolve this. Should be process. I think. Yeah, I think this is going to be a process control full guard policy. Yeah, it's a process control full guard policy, which means that we're the control full guard policy of the process. It's checking the control full guard, the policy of the process, and v22, which should be the last here. This is a puffer. That one actually accepts 3 parameters. But anyway, this is a puffer, definitely. I think it's yeah, so when this process control flow guard, the policy parameters specified. The puffer receives a pointer to this process mitigation control flow guard um, uh, the policy structure. So I think we need to just retype this. Uh-huh. So it's actually checking the flags field, which maybe indicates whether or not control flow guard is enabled for this process. Uh, let's see. Look at the definition here. Yeah, flags here. This member is reserved for like system use. I think it should check for this flag here. See if she enable for this process if this flag is set. I think it should be checking for this flag here. Just to begin with. Whether this one accepts like a force parameter. Let's retype a function. Uh, I don't know, but it's like I assume this should be a pointer. Um anyway, this could be a typo or something. I'm not really sure about it. You know what? I can check the uh, annotated IDP file. Let's do this. I think I have it here somewhere. Got a file explorer. So I think it's here's um I think again this is the this is the decryption INDL name currently. Yeah, so we're actually here. Yeah, this is an input injection. This is the branch we didn't take because this flag was to begin with just like a false. So I think this is gonna be yeah, it's like checking the flags. Huh. Um yeah, okay, it doesn't matter. We know that we're doing it right. I don't know, it should be checking the other flag, but it doesn't matter because it says this flags here should be anyway. we know it's checking if control flow guard is enabled here. Actually, regarding control flow guard, I've got this really nice paper on what control flow guard really is. You can see it's a mitigation technique introduced with Windows 8.1 preview, but then they disable this for the to manufacturer release the manufacturer version for compatibility issues. But then it was improved and enabled in Windows 10 technical preview. And pretty much mainly the way control flow guard operates is it prevents any in-track function call or in-track call to a non-valid address. What that means is we have this, guard control flow check function pointer, which is by default initialized to this loader validated user call target function. And so this is a function that's meant to be invoked before an intract call to any address. And an intract call, in case you didn't know what it is, it means that we're like moving an address into a register and we're calling to this address. Like it's like moving maybe an address into RCX or RDX, then say call dealer pointer and brackets and RCX, which means we're calling to whatever's the address stored inside of this register. This is what an intract call is, and you might see this so often in maybe C++ because we have these objects which have VF tables, and these VF tables define virtual member functions which are stored at offsets relative to the beginning of the VF table, and so you're expecting to see a lot of intract calls whenever you're dealing with C++. And so for this loader validated user call target, actually let me show you the definition of that function. I think I've got it here. Oh, it's gonna take a while to process. Oh, it's here like doing this. Let me show you. When you have a move of maybe let's say RDX, knowing that RDX points to some C++ object, and so RDX here is just a CBP object pointer. It's an instance of a class, of a C++ class. And so in RDX here, usually the first member of any C++ object is going to be the VF table. I mean, if this object defines virtual member functions or inherits from other classes that define virtual member functions, then this hidden first member is going to be the VF table pointer, which is a pointer to a table of function pointers. And so this is the object pointer, or you can say this is the VF table pointer. So we're moving that into RCX, and now we have a pointer to the head of the VF table, and we can use that to access just any other, virtual member functions. So you can see like maybe a call to RCX, or just the word pointer, and then RCX offset 8. So this is calling whatever is the member function at this offset from the VF table. So yeah, that's what an intract function call is. This is intract. And so before this call is made, you should be able to see another function call, which is this function called oh, excuse me. I think it is yeah, that's it. yeah, I should be able to say equal to that function with the address pointed to by RCX plus 8 passed into that function. Just to validate that this is a valid address within the valid, within the, what is defined as a valid address range. So I'm sure you can like maybe look more into this, but we didn't need just to know this much about it. So I just want to go to this function, and inside of this function, we have this other function, which is the loader handle inval user called target. And so this is the function APT41 StealthVector is trying to patch back. And I'll show you how it does this. So having confirmed that it's actually you know that it's actually enabled and validated that the operating system version it's running on is a CFG control flow guard aware system, because I think here if that is not a control flow guard aware system, then we're probably not gonna buzzer check in if CFG is enabled. But I think here for our purposes, this is the check of control flow guard and how it patches that function. You see here these two unknown pipe pointers. Let's take a look at that one here, and to see what appears to be a pipe sequence, which is 42153, 42152, etc. If you just look inside of that function here, and let me show you the opcodes. Yeah, you see this is pretty much the exact same pipe sequence we're looking for. Let me side by side these here like this. This is 42153, 42152, etc. So this goes all the way up to the 80000. So yeah, the 80000. It even goes past this. You see the 0F29, 44, 24, 20. So it goes up to here. So it's actually checking for the function or just locating the function PySertion through the binary for functions that's stored with this pipe sequence, I think. So this is the pipe sequence we're going to be looking for. But again, that depends on the operating system version, because you can definitely see another cool to RTL get version, because different operating systems may have like different versions of NTDLLs, which means different pipe sequences. So this pipe sequence will be for another I'm not sure, but we can actually check this out here to see and let's look at the um I think here we were looking, yeah, that's it. Yeah, so uh this is actually checking like the build number check when is 10.0 or later. This is the pipe sequence for when is 10.0 and later, definitely. And this is for maybe when is implementations before when is 10.0, like when is 8.1 or something. So I think that's pretty much it. If you look at that here, this is gonna walk the text section and try to locate that function which has this pipe sequence. How do we know this? Well, you see the get module handle which retrieves a handle to the NTDLL. But then again, let me show you this here in our so this is getting a handle to the NTDLL where the target function is actually implemented. Um, then you see adding offset 15, but this is not 15. This is where side by siding the decompiler view was the disassembly comes in handy because you're gonna be able to see things that the decompiler might get wrong. This is adding offset text C, which, as I told you before, this is the NT headers pointer. So we know this is the NT headers, and we're adding this to the module handle, which is the base address, and then offset 108. So offset 108, I believe this could be just a pointer to the section table or the section header table, because I think the file header is like fixed in size, like hex18 bytes or something, and we're adding the size of the optional header to this to get the section header table. And so yeah, this should be your section header table. I can just rename it to section table. And so you see it's like looking for the text section, obviously. And as soon as it finds this, it's gonna pretty much examine this for the proper byte sequence uh, based on the current OS version. So that's how it locates this function loader user whatever. I didn't get the name actually. It's loader p handle invalid user called target. So yeah, having located that function now, I assume this is gonna be the function pointer. This should be your function pointer. This is pointer to this function. Should be pointer to this function. Yeah. I think again we see the same sequence of APIs we've seen before with ETW patch. It's using the permissions to execute read write execute, so we can just write the patch bytes to the function. In our case, these bytes are, again, we can just write a code. Yeah, this is a jump or a accident and an interrupt. So it's actually jump into the address in REX and just this is really just the let's just call it so this is the control flow guard patch thing. It tries to locate the function that will be called by the other function that validates whether the address is a valid call target or not. That's how it patches CFG or control flow guard. So yeah, that's really it for CFG or control for guard. I think here this one is the one that implements the uh, process following thing. Excuse me, not the process following, the module stomping thing. I'm gonna actually continue from the annotated file. I think it's just a lot more easier. Um, yeah, that's just the patching the first 5 bytes of the function. Interesting. Well, now, this is, yeah, so, but where's the, yeah, I think that's it. Um, so for this function, we have a memsat, and we have this other function here. Let's, take a look at, yeah, so, this is really a very big and large function. But let me walk you through this real quick. You can see it retrieves the handle to the kernel 32 DLL, and we're using that to resolve or get the address of the get system directory y character function, which is pretty much just C1 system32. This is where system libraries like DLLs and drivers are in Windows. And I can see here this is like walking to the end of the buffer. So this is the get system directory. This is gonna be where the system, this is where C1 system32 will be written, obviously. A memsat, walking to the end, etc. All right, let's see. I can see this \asterisk.dll \dll, and you can see find first file here. Where's the find next file? Yeah, find next file. So we know that we're doing a file enumeration search. It's just enumerating the system directory for files, for specific files, and I'll show you this in just a second. So it gets the passive system directory. And then again, I think this is gonna be your, if you look at the find first file function, it should take the file name, and that file name in our case happens to be, this is like v15. Yeah, I think it's gonna be like a \asterisk.dll. So this is the pattern that we're looking for. We're looking for any file that ends with the .dll extension under the system32 directory, which is where system files are. So this is, like I said, enumerating system directory for DLLs. And you can have, let's see, this returns a file search handle. And if this is like an invalid handle, we can just rename that or map it. Yeah. Then we have this while true loop here. And you see this is the get module handle y character, which the file name passed into that function. So this retrieves a handle to whatever is the DLL we currently have access to under the system32. And then we're checking the name against a list of blacklisted DLL names. And so this is something like I haven't seen before. It's trying to avoid like tampering with these system DLLs, because these are the ones that possibly implement critical system functions like cryptography and stuff like that, networking communication, etc. And so if it's this is actually the string comparison thing. This should be the name we just pass into the function. This is converting to lowercase, converting lowercase. I think lower, not uppercase. Yeah. Yeah, interesting. And you can see if if the module is any of these blocklisted DLLs, then we return a 1. And so we don't want to actually process or mess with these modules or DLLs that are blocklisted or could contribute to critical system activities. And so we're trying to avoid messing with these, because basically what DLL hollowing is, it's going to find a large enough text section in a system DLL on our system 32 directory, and it's going to load up this DLL into memory and inject the payload into that DLL. And so it's actually injecting the payload into the address space of a large enough text section of a DLL that's not one of these. So I hope this is clear, but we'll see actually more. So yeah, I think here you see this is how it knows whether or not it's got like a large enough text section. I think this is trying to find the text section. So I think if it's not if it's none of these plot listed DLLs, and it reads like the first text 400 plots of the DLL, checking the characteristics to make sure it's a DLL, because usually DLLs have this flag here. I think that indicate that it's a DLL. Yeah, I think this is the flag here, the hex 2000. Making sure we have 4550. That's just the PE string of the P headers, and so making sure this is a proper P file. Then we're locating the text section. Then we're making sure this is a large enough text section. Uh, um, so not only we're trying to locate a DLL, like I said here, it means that we have fan and a large enough text section that can house our shellcode. Yeah, I get it. And so we're, this is the size of the decrypted payload that was passed into the function, I think as a parameter. And so you see this is actually, this is checking the physical address. Actually, this is not physical address. This should be virtual size. It just, this miscellaneous field is actually more of a union, which like offers like two multiple different interpretations of the same piece of data. It's now no longer interpreted as physical address, but as size of or virtual size. So we're checking the virtual size of the text section to make sure it's large enough. And the adding of 4T96, which I believe 4K, which is the size of a page, just to make sure it's a page aligned value. So that's, I guess, what we're trying to do here. We're enumerating the system32 for all these, DLLs that are not plot listed. Once we find that not plot listed DLL, we are checking the size of the text section to make sure it's large enough so it can house our shellcode. If it is, then you see that we return a pointer to the target DLL and its text section as well. That's for this function here. I think here copy full pass. Interesting. Let's go here. Once we found this large enough text section of the DLL, we're gonna load the target DLL into memory, and look what we're doing here. We're gonna change the permissions again to hex 42, which means page execute read write. So this is page execute read write. Again, why we're doing this? Because we're gonna be writing our encrypted or decrypted payload into that memory of the DLL. So this QMM copy just copy the shellcode into the region of memory into the target DLL, and that's it. So I think that should be really it. That's just what I wanted to cover for this loader. How it just disables control flow guard. How is it able to try to locate this target function, loader, handle, whatever. Yeah, but by insertion the text section of NTDLL to the byte sequence, the proper byte sequence based on the operating system version. And once it finds this, it's just gonna patch it to make it return prematurely. Also the DLL or module stomping technique, which is finding a system DLL that's not one of these critical system DLLs with a large enough text section to inject our shellcode into, then transfer execution over to this. So I think that's pretty much it for this video. I'll be uploading maybe the this paper on control flow guard. It's very interesting read if you want to understand more in depth how control flow guard works. But this is as much as we need to know about it. As for how it works, how it validates was it's a valid target address or not. But I'll upload it as well. And so, yeah, I think that's pretty much it. So thank you for watching.